Welcome to the Power of ERDC podcast. I'm your host, Shelley Tingle with the U.S. Army Engineer Research and Development Center. What if stronger levees could begin with healthier roots? Today, Dr. Lucas Walshire of ERDC's Geotechnical and Structures Laboratory explains how biostabilization uses biopolymers and vegetation to reduce erosion, improve overtopping performance, and potentially prevent costly slough slides. Welcome, Lucas. So, for our listeners who may not know about or be familiar with the technology behind biostabilization and why it is important for levees, can you give us a little bit of insight about biostabilization and levees?
Sure. Well, we used a biopolymer, and it's a naturally occurring substance that forms a symbiotic uh, relationship with in the rhizosphere with roots. And so, it's naturally occurring. You're not putting in a foreign substance to the soil. You're just giving it a boost with these biopolymers that, are there naturally anyways, sequestering heavy metals, improving soil water retention and drought tolerance and those sorts of things. And so we found that it was a good alternative to commercially available or traditionally used soil additives, and has the potential to be economically viable and provide long-term improvement to the embankments, and hopefully mitigate a few of the common failure modes that impact them.
And so, why is ERDC uniquely positioned to solve this problem?
Well, we're unique in that we have these laboratories, the environmental laboratory, the geotechnical laboratory, and we are all, in the same boat. We work together well. We have the facilities to carry out this research in a very economical manner, and optimize these different. We could do a greenhouse study per se, or do a geotechnical laboratory investigation, understanding the impacts of erosion or shear strength, those sorts of things. So our facilities are world class, and then having the personnel on site that can work together and have the experience and education to carry out this research is very fundamental.
So, traditional soil stabilization, um, we all know about the lime and the cement. And so, why is ERDC investigating biopolymers as an alternative? Why are those methods no longer viable, or why do we need to change?
Well, uh, production of lime locally is really not occurring anymore. We're importing a lot of those, and so there's a big strain on the market, and so as a result, these prices have been increasing to the point that repairs done to levees, maybe they just put it back and they don't use an additive where they really need to, just because A, the lime's unavailable, or B, the cost is so extreme that they can't fit it into their budget with the number of projects that they have. And so biopolymer provides a viable alternative because it's uh, can be produced in an economical manner, and put into the ground, and not leach away and provide longer term impacts where lime may leach over time.
Very good. And so, what is the biological process that allows the biopolymer to improve this relationship that you mentioned between the soil and the roots that are and the naturally occurring microorganisms?
Mhm. And so the bacteria in the soil, they're just there uh, naturally produce this because they want a healthy environment to live in, right? So you get this symbiotic relationship between the roots and the bacteria, and when they're stressed, will produce this biopolymer to help with, like I mentioned, soil water retention, which is just how much water is retained in the soil compared to the surrounding soil where roots aren't present. That would just dry out. Also, where there's heavy metals or pollutants, it's in the bacteria's best interest to, provide somewhat of a shield to the roots. I'm a geotechnical engineer, not a biologist or ecologist, but that's, my understanding of it. And when we add biopolymer during construction or rehabilitation, we're giving a boost to the seeds we're putting in the ground, whether it's native seeds or whatever that get a head start. It's not a fertilizer, but it helps germination, and this bacteria, will eventually consume the head start we gave it, but it's also kind of infected the roots and promoted an increased lateral root growth that results in a really dense root mat, helping with what we found was surface erosion, overtopping types of erosion, and we postulate that over time it'll decrease the shrink swell of high plasticity clays that often result in slough slides and those things, especially in the Mississippi Valley and anywhere you have a levee or embankment constructed of fat clays.
And so that's one of the beauty of Power of ERDC, of our ability to bring in other subject matter experts that are right here at ERDC. So like you said, hey, I'm not a
Right, right,
I'm not a biologist, but hey, I know one.
right. Exactly, exactly.
And a lot of times that's what matters. And so you described both the short-term and long-term benefits. How does biopolymer initially improve the soil behavior, and how long does it take before that vegetation starts providing the protection?
Right. With the research we conducted, we did a laboratory and a field demonstrations. And what we found in the laboratory, you need a little bit higher concentrations, but you can dramatically decrease the hydraulic conductivity, which is important for seepage, increase the shear strength, which is important for stability, and then, minimal impacts to compressibility and those sorts of geotechnical parameters that we're interested in. But these are short-term improvements. Like I said, the bacteria are going to consume this biopolymer, but it's forming chains between the particles. But that's a short-term benefit. The longer-term benefit is the interaction with in the rhizosphere, which with the roots. We worked with material scientists in our research, and they found that they use the word infect, which is not always a great connotation for the rest of us, but it basically stimulates lateral root growth and the bacteria, I believe, wants that healthy environment. They want a lot of roots in there holding the soil together, um, and promoting just a healthy rhizosphere. And from an engineering perspective, that's good for us. We've found some longer term studies that those persist, that dense root mat, which is at the ground surface down to, up to a meter in some instances, can really provide, the first line of defense when you get a levee that's overtopping due to floodwaters, or you get surface erosion, or even potentially slope instabilities.
Wow. And so, what specific levee problems is biostabilization designed to address? So, you mentioned a little bit about the slough slides and some of the overtopping erosions. What does it help? Does it help with breaching? What are the other problems that it can help address?
It's the first line of defense. You still need to do good levee practices, taking care of making sure that critters aren't digging holes in your embankment and that sort of thing. But it's what it really is that kind of outer shell, providing that, as the floodwaters go over, maybe you not necessarily getting a breach. Your levee's still going to be there. Just because it overtops, isn't the end of the world. You can still minimize the backwater rise and those sorts of things. So really, overtopping, breach, head cutting, really prolonging that time you have. And then also, when a river is parallel to a levee, maybe a silty sand like a Sacramento type levee, it has the potential to prevent that type of erosion as well, which is a major concern for those kind of intermediate soils. And then, of course, I mentioned the slough slides, which we're still working on different demonstration sites to prove that hypothesis and those sorts of things.
Very good. And so, you mentioned that you this is really good for those clay areas
Mhm.
around where we live in Mississippi. But are there other levees? Can you do it with silty or sandy soils? Is this applicable to all levees or just certain levees?
As you're probably aware, a majority of our levees in the Corps Engineers inventory and our partners' inventory are constructed of lean or fat clays or sandy
That's
clays,
right.
those sorts of things. But like you said, the silty sands and the clean sands, where maybe in the upper Mississippi they used to repair a breach that's happened in the past, are very susceptible to erosion and overtopping breach if they do get overtopping. So we're working with partners in those districts. We focused on our research in the clays and we did a little bit at the laboratory scale, but now we're going to that transition to these demonstration sites and those kind of what we call intermediate soils, the smaller minority of soils that we have in our inventory that are silty sands or sands. So we're still working that out, but from what we've seen, looking at what the Koreans have done, they do quite a bit of research in this realm as well, that it does have the potential to do that.
That's amazing. So, can treatment be applied to an existing levee, or does this have to be part of the original construction?
It can be both. Is what we did. We did a demonstration site on the Mississippi rivers and tributaries levee embankment south of Vidalia, Louisiana, and as an existing levee, of course, that has a history of slough slides. And we did 5 demonstration sites just to test the scalability and how constructability of it as well. And so we were able to do that. We have some methods that we've kind of refined with a few other demonstration sites. So yeah, to answer your question, we could do it both as a rehabilitation effort to an existing levee and also to a new construction as well.
Right. So you're talking about solving problems across the core when you're talking about levees of being able to do it
Correct.
from the beginning or gosh, all the existing levees we already have.
Mm.
So that's amazing. How quickly does the treatment become effective? And how important is the growing season to establish the vegetation and root system?
Mhm. Because it's you're working in collaboration per se with the vegetation, you really need to hit that growing season. The around here it's March,
Mhm.
April, maybe April, May up north. So that's important. And if you have a drought that first year, it's going to adversely impact. And we found that on one of our sites that you still need to have good practices and good luck, as any farmer would tell you with regards to that. But about one growing season, we found we did an overtopping demonstration at the end of the initial research, and that was after one season, and found a pretty good impact where the non-treated levee breached while the treated was intact. It did incur
Right.
erosion, but it prolonged that sort of lengthened your fuse, so to speak.
Right. And so with such I mean, so that's pretty rapid. I mean, one growing season is pretty short. And so what were the effects, let's say 2 to 3, 5 growing seasons out?
That's what we're still investigating. The demonstration site south of Vidalia that I mentioned on the MRNT, we're just kind of getting at that point, and we're at the end of our remote monitoring kind of plan, and we're still seeing differences in the soil water retention, which is what we were using
Mhm.
to measure plant health, where you were retaining water and reduced suctions compared to the untreated sections. So we still were seeing an impact. Um, and there was an embankment that Dr. Larson over in EL had treated up in Burlington back in 2012. It was ammunition berm. We went up and did a follow-on investigation 10 to 12 years later. And, the roots, we had trouble getting samples because the root mat was still so dense. And that was like a fescue that they were using. So it was
Wow.
a really good result. Granted, Iowa has really good, soil, but it still worked really well.
Wow, that's great. And so how has ERDC tested this technology in the laboratory? You mentioned that a little bit earlier in this conversation about our facilities.
Mhm.
And so how did you do the testing and in the field, including full-scale levee overtopping demonstrations?
Mm. So initially we tested a little higher in the laboratory, and following the greenhouse experiments that we conducted in partnership with the Cold Regions Lab and worked with the environmental lab as well, we found that actually an optimized dose is quite low to get started when you're seeding, and you would still see the same benefits. But in the laboratory, we have a research geotechnical lab. We would treat on big trays and try and mimic how the conditions in the field. And we did triaxial UU, CU, consolidated undrained, unconsolidated undrained tests, as well as some direct shears. Testing both the short and long term impacts. Did hydraulic conductivity testing and traditional sort of geotechy type tests. We wanted to see the difference that were going to be had in the short term. And then we also did some innovative things such as taking Shelby tubes and trying to, mimic the field by getting, having a little greenhouse that we set up and playing ecologist and getting the turf to establish and then doing uh, using the erosion function apparatus to test for the erodibility of the soil. We also did some of that in the jet as well, trying to, really just use our wide variety of resources to define the impact to the turf.
That's amazing. So, you mentioned little bit ago about obviously you didn't want a drought to occur when
Right.
you first put this in. So, how does biostabilization perform after that first growing season? How does it perform under these extreme weather conditions that we're seeing of droughts, like we have here, extreme
Right.
heat,
Right.
or sometimes here too, not often, but freezing temperatures
Right.
where you would see higher up in the upper miss, or even what we see here a lot in the spring is prolonged saturation,
Right.
going into the high river marks. And so, how does biostabilization perform under all those conditions?
Yeah, so we reached out to some academic partners, excuse me. We worked with Iowa State University, and they did some freezing tests. They had some innovative approaches for understanding the impacts, the geotechnical impacts under freezing conditions. Found that, had good results. And like I said, the Burlington sites in southern Iowa says you're aware that it gets very cold up there, and performed well over those multiple seasons. And then, under the drought conditions, we had a little trouble because we did have a drought that first year that we applied it, but um, once we got it established, the turf established, it really took off. And then as a follow-up, we did a transition phase. We worked with the Vicksburg district and applied it to a silty sand in the headwaters of the Grenada Lake. There they have a man-made channel, and we're actually gonna it's been the first year, so we're gonna go do a detailed investigation this fall to really quantify those impacts. And we worked with the Levee Safety Center to use native grasses in conjunction with the biopolymer to see if we could have that impact using, what's native to the area that has the potential to decrease invasive species. So,
Oh, wow. And so it sounds like that Erdic is obviously researching all those things,
mhm.
but that so far the results are looking really good for
Yeah.
biostabilization. And so, how does this approach compare to more traditional erosion protection methods?
Mhm.
I mean, I grew up to where riprap and geotextiles were what we use. So, how does it compare to those traditional methods in terms of performance,
Mhm.
cost, maintenance, and appearance?
I think, especially for levees, riprap can be very cost prohibitive for longer stretches, and lime, the same as we discussed earlier. So it has the potential to, healthy vegetation. I believe the community, especially in residential areas like, that visually appealing green grass type
Right.
of levee. And, it helps to, promote that healthy sense and, psychological kind of reassurance that our flood control embankments are healthy and vibrant and that sort of thing.
And so, what if you have which? I guess the better way of saying this is which levee owners, use districts, local levee boards, or private embankment owners could benefit from this technology?
I would say all of them, as a potential. We're working with multiple districts in multiple areas, as I mentioned. Rock Island, Memphis, uh, Vicksburg, New Orleans, all up and down the valley. And then we have some plans to reach out a little further. But I think anybody with a levee embankment that is interested in this kind of approach, it has the potential to be cost effective and has right application. It's not a magic bullet or anything like that, but it does have its application and has the potential for long term improvements that it
And
can
so,
provide.
if I'm sitting on a levee board or I'm a private embankment owner and I'm listening to this podcast and I'm an industry partner and I'm like, I may want to get in on this. Did they just reach out to ERDC and partner with you?
Yeah, we've with industry, we put a couple calls out for with Erdic Works for kind of RFIs to see what if they could, develop,
Mhm.
these relationships. And so we're working with a few external partners on that as well to really kind of we're in the transition phase where we're kind of intermediate demonstrations and under different conditions to really define those design parameters that are important. But yeah, reaching out to Erdic right now would be the best approach.
And so just talked about how you're moving this research towards implementation. What demonstration projects or specifications, product capabilities, industry partnerships are needed to move this towards implementation?
I think, there are commercially available biopolymers that are just fine and well documented. We actually used a locally sourced biopolymer and found that, you know, it can be really cheap to produce and to produce in mass that, trying to get those regional suppliers stood up, would probably be the best approach. And it's not expensive to produce. It's, basically growing bacteria and stressing it slightly. So that would be probably the biggest challenge there. The commercially available we found still are economically viable and you can source it to some scale. Um, but yeah, I think that would be the big thing, and then understanding with our like I said, we have numerous demonstration sites up and down the Mississippi Valley that we're working on different conditions. We'd like to branch out west to understand those sorts of applications as well. So those would probably be the 2 hurdles I see right now.
Very good. And how can an agency or academia, you mentioned some of the research that you've done with Iowa, levy owners, industry partners work with your team on future demonstrations or tech transfer efforts?
I think just reaching out,
Yeah.
and communicating with us and we can work to incorporate anybody, yeah.
And so, one of the biggest things that I found very fascinating with biostabilization was the logistics of you mentioned about the lime and the logistics behind that, about the cost of it, and sometimes it's not locally available. So, explain to our audience the biggest thing about biostabilization is logistics and cost cutting savings over time. So, can you dive a little bit into why this is so effective and is going to save the taxpayer dollars at
Mhm.
the end of the day?
I think it's a there's no reapplication, in the near term. I mean, you may down the road, it's not gonna hurt it. But you're, given the right vegetation and the right good practices, application, has the potential to really, once you get it going, it's gonna be healthy and vibrant, over the long term that we found that 10 to 12, still going strong and hadn't failed, that potential. So I think that's the biggest thing is that, with lime or cement, more often lime, over time you may have to go back and repair it, after it
Mhm.
leaches out and that sort of thing. And also it's hard if you do too high an application of lime, it burns the soil. It can't grow. The pH is too high or low. I can't remember which, but those are the biggest thing. And then also it can be locally produced. Uh, and put out there. You'll read in the literature. I mean, everybody's kind of got their own little concoction they're putting together, but and it's easy to scale up. And that's what, our partners in the environmental lab found that they were able to scale up very rapidly and produce it in quantity that we needed to um, apply. Yeah.
Wow. And so at the end of the day, it's saving the taxpayers a
Mhm.
lot of money.
Okay.
because it's reducing the maintenance and it's easy to install. So, can you tell us a little bit about when you're treating these levees, what type of expertise is required compared to the traditional methods of maybe riprap or some of these other methods?
I think, when I mentioned the demonstration site with the Vicksburg district, so as a transition, we really wanted to see if the local labor and operations could install it. So we provided the biopolymer and gave them kind of a set of instructions and gave them, seed choices because obviously it's not always that they're using native seeds, and they didn't need any special equipment besides the biopolymer, right? And it was all in their wheelhouse, and they were able to do it, and they successfully planted, and we'll see this fall, as far as the detailed nuts and bolts of it. But there's no specialized equipment that typical districts don't already have.
That's amazing. So you're already using the equipment and people that they already have in place. And so, again, reducing costs at the end of the day of using this biostabilization method. And so, is there anything else you would like to share with our audience before we end this podcast?
I think just, kind of surprised at the longer term benefits and the potential for it. I was skeptical when we went into this research, and seeing some of the results, I'm optimistic that we can, provide a economically viable alternative, that various practitioners may want to use and hopefully do.
Absolutely. And so, I want to thank Lucas for being here today. Thank you, Dr. Walshire, for taking time out of your busy day and out of your important research to talk about some of the exciting things that you and your lab and your cohorts are doing. I want to thank the audience for watching, and thanks for joining us for this episode of Power of ERDC. And to learn more about ERDC's biostabilization research and opportunities to partner with ERDC, just visit the links in our show notes on our website at poweroferdicpodcast.org, poweroferdicpodcast.org. And if you have any questions for Dr. Walshire, you can also email us at erdcinfo@usace.army.mil, erdcinfo@usace.army.mil, and all those links will be in the show notes. Thank you.